Hi everyone, I'm Abigail Zimmerman-Neefield. I'm from the University of Colorado Boulder, and today I'm going to talk about youth learning machine learning through building models of athletic movements. Before I start, I'd like to acknowledge my co-authors, my lab mates, the University of Colorado Boulder staff who contributed to planning and logistics, and the gift from Google that funded this work. So, why are we talking about machine learning today? Technology that uses machine learning is pretty common, from conversation agents to smartphones, smart watches, smart homes. In fact, there have been a number of contributions to recent IDC conferences, including this year, about children interacting with machine learning technologies. Here are two papers from IDC 2019 about children interacting with smart homes and smart watches. But what would it look like for children to develop literacy and creative agency in machine learning? And by that, I mean, how can kids develop an understanding of the machine learning rich world around us? And how can kids use machine learning as a tool for creativity, making, and play? Usually when we talk about machine learning, we're talking about advanced undergraduate or graduate students in computer science. But you don't need to know how to code to learn how to apply machine learning to problems. We don't know what this might look like. We're just at the very beginning. 40 years ago, people didn't yet know what exactly it would look like for kids to become literate about computers or to learn how to code. But now I've said machine learning 4 times, so what is it? Applying machine learning is not coding an algorithm. Coding involves writing exact instructions for the computer to execute, whereas applying machine learning involves collecting data and specifying how the computer should draw inferences from that data. Both processes involve testing and evaluation. There are kinds of machine learning that don't involve these steps, but in this talk, I'm just going to talk about applying supervised learning. So here are the big questions I hope will be addressed in research in the coming years. How can new tools support youth building machine learning models? And how can learning of machine learning be anchored in young people's existing knowledge, activities, and identities? So with that in mind, here's what I'm going to cover today. I'm going to share with you a rationale for designing tools with which kids can explore machine learning. I'm going to present our beginning exploration into youth novices constructing machine learning classifier models of their own athletic practices. And then finally, I'm going to share our agenda for future research directions. We designed Alpaca ML to help us start to answer some of these questions. And I'll show you it in action after we've trained a model, and then I'll show you how we got there. So I'm kicking a soccer ball against a wall.
Good.
And Alpaca ML says good when I make a good pass and bad when I make a bad pass.
Bad. Good. Bad.
So it's classifying my kicks. Why are we doing this? First of all, many kids care about sports and already have a ton of knowledge about them and what makes certain actions good or bad. We also believe that machine learning is well suited to practicing repetitive motions with the goal of self-improvement, and especially if you add a coach who is an expert in real-time feedback that can guide improvement. There are 4 key parts to this: the athlete with the knowledge, some sports equipment, which in this case is just a ball, a sensor, that's what's on my ankle, and the phone. For the sensor, we use a BBC microbit. It has a built-in accelerometer that streams data over Bluetooth to an iPhone. Here it is up close. Then the athlete uses the mobile app to facilitate an interactive machine learning process as described by Rebecca Fiebrink in her work in the area. The athlete uses their knowledge to identify skills to improve and decides where to place the sensor on their body. Then they go through this iterative process of collecting data, labeling it, testing their models, and evaluating their models. After they've reached some level of performance, they begin to use the model in practice. So first, they use the app to collect data from the sensor.
Recording.
Okay, great. They can play it back and watch how acceleration changes on a synced graph like this. Then, they can select segments of the data and label them with the classes good, bad, or no action by tapping and dragging on the graph like this. Then, they can test out their model, and it will speak out the classification in real time.
Bad.
And then they can evaluate and edit their training set by selecting and deselecting segments. Alpaca ML uses dynamic time warping, a classifier algorithm that finds an optimal matching between two time series. For example, a series of three-dimensional acceleration like the one we have. We conducted a 2.5-hour pilot study with Alpaca ML, which we advertised as a sports wearables workshop. Participants came to try to create their own sports wearables. They spent the first 15 minutes just playing around with the sports equipment that we brought, an hour learning to use the app by modeling soccer passes, 45 minutes working on modeling a sport of their choice, and 30 minutes debriefing in a focus group. Our participants came from local high schools and sports teams. We had 3 girls and 2 boys, all ranging from the ages of 13 to 17, and all with different sports experience. I don't have time to present you all the results we share in the paper, so I'm going to focus on a few key ones. Participants engaged in realistic, meaningful exploration and creation with machine learning. What do I mean by that? By realistic, I mean that their practices were reflective of typical machine learning practices. And by meaningful, I mean the practices had personal relevance to them. That's what I'm going to focus on as I'm showing you clips. So, as I said, we started off by training soccer. We scaffolded this for them to simplify steps 1 and 2 here. We told them to place the sensor on their ankle, and we told them what to call good and bad passes. So they were able to jump right into the data collection, which is what you see here. In partners, they recorded data while kicking the ball at the wall. I partnered with Farley because there were an odd number of participants. So I already showed you the labeling interface. So for time's sake, I'm just going to skip them using it. But here's the interface just to remind you. After data collection, they moved on to testing their models. So we had asked them to test and evaluate their models, and I'm going to focus on one of our participants, Farley. We had an odd number of people, so I'm recording the results for her again. You'll see that she kicks the ball, and then the app calls out either good or bad. Was that actually bad, or was that a good one?
That was supposed to be a good one.
Okay. How about that?
That was supposed to be a bad one.
Yeah. Just yell out.
Good.
Once Farley tested her model, she moved on to evaluating it. In the next clip, you'll see her evaluating the results of her test and coming up with a plan to improve it.
It's probably good to have the same amount of good and bad data points, because I know there's more bad than good in here.
Why do you think that, like, relative amounts might matter?
Just because it has, well, more options for what qualifies as bad, and, a more selective view of what's good.
Got it. So what does that suggest if you want to make one? Well, I'm trying to remember, what was better or worse about the model? Like, what did it do well at and poorly?
Last time it did really well at identifying the goods, and that's when we had more good data points. And this time it did really well at identifying the bads, and we had more bad data points.
So what does that suggest to you about how you might change it?
Try and get it equal.
Okay.
And try and get it really well selected.
Okay.
This video, I believe, was on her third iteration, so she had already made it around that spiral a few times with soccer. And you can tell she's developed a sort of theory about what happens when she has different numbers of data points for each class. We saw several participants do this, develop hypotheses about why their model might not be performing as expected. After we taught the participants to use the app through the soccer example, we let them identify their own skills to improve. And I'm going to show you an example from two sisters, Sally and Jamie, who both play softball. They picked their main sport and they drew on personal knowledge of it to develop their models.
So a good pitch, I guess, would be if the seams are spinning. But if the seams aren't really spinning all the time, you can't really see the spin. It's not
Which is usually determined by the snap.
They specifically focused in on a wrist flick, as it turns out. And here's Sally explaining the mechanics and giving a little bit more of a demonstration.
So I'll just do it like to myself, I guess. Good motions like that, they spin a lot.
Okay.
So that motion would be like that.
All right, kind of just like, what's, I don't know, like the lobs a little bit.
Throughout this part of the workshop, the participants continued to iterate on their models and develop theories about what they built. Again, I'm keeping it to these short examples for time's sake, and you can read more about what happened in our paper. But here's a brief overview of some interesting things we saw. So I talked a lot about this first one. Participants were able to define, build, evaluate, and iterate on models of their athletic skills. We also saw participants overfit their motions to the models that they built. And finally, they also developed, not necessarily correct, but theories nonetheless, about how to build good models. So what's next for Alpaca? Well, we'd like to add multiple sensors. Certain motions are complex and require multiple body parts, like this cheerleader who's about to do a front tuck. We'd like to provide kids with multiple sensors so that they can use Alpaca ML with more complicated motions. We'd also like to add cross-validation. As kids get more sophisticated and want to be able to better evaluate their models, we need to support them in that. And finally, what if kids had a choice of k-nearest neighbors, dynamic time warping, neural nets? We think that would allow them to build more and learn more. There are a bunch of directions where the IDC community could go with kids learning applied machine learning, and here are a few. We could use Alpaca ML in other domains. For example, it could be used to enhance artistic performance with the body or to enhance interactions with smart homes. We could, in order to do things like this, users would likely need to not only apply machine learning algorithms, but combine them with coding to script interactions with networked objects in their environment. And then finally, what does it look like to get better at this over time? I showed you examples from just the first few iterations around that spiral. But what does it look like on the 10th or on the 100th? So, in conclusion, machine learning can be a part of the expressive toolbox available to youth, and it's time for more research in IDC and elsewhere on how to make that possible. You can check out our lab website here, or shoot me an email or find me on Twitter if you have any questions about this. Thank you.